All right, let's talk about what we got here now. I do want to try to record here, but we have some stuff on the board. So essentially, what we see on the board here, we've got these volume or these slices, and they're kind of cylinder-shaped slices. But we're saying that each slice, if we look at this, here's the x-axis. Each of our lemon slices kind of looks something like this, where this height right here, that's kind of the radius. Now, we did say that there's two different radius because of the slice. But imagine, of course, and you know, as you read down there, what if, since they're not really cylinders, we had to do an average to kind of get the volume of each thing. Now, what happens if instead of 6 slices, we did 10 slices, as you read there, hopefully towards the end, or 100 slices? What would the shape of them be? It'd be a little more like a, I mean, they'd be the same shape, right? But they'd be a little more like a cylinder. So as those slices get thinner and thinner and thinner, they'd be a little more like a cylinder. You know what I mean? Like the radius, this radius over here and this radius over here would basically be the same. Those two would be coming towards each other, right? And as you went to an infinite number, if the slices got paper thin, then they would be like little cylinders, almost like circles. I mean, if they're paper thin, they'd be just like circles where the width, the h, would be going to what? To 0, right? So an infinite number of slices, the h would be going to 0. Well, and we said the h is like the delta x. And what happens when we do an infinite number? What happens? What do we say? The delta x turns into the dx, right? In other words, so what we're doing is adding up the volume of slices. Well, gee, it's too bad we don't have something that will add up an infinite number of things. Oh, wait, we do. It's called the what? The integral, right? Sigma will add up any, like 6 things, 10 things, whatever. But if we do an infinite number, it turns into an integral, right? So remember we did that with arc length. We said we have these little pieces of length, but we want to make them smaller and smaller, and we're the integral will add up an infinite number of those little lengths. Well, how are we going to find volume of a solid? We'll use the integral to add up the volume of an infinite number of little slices. But what we need inside the integral is we need the equation of the volume of each slice. So let's start with the sigma. So what you had there, they said, well, what would be the volume for 10 slices? Now, we can get real fancy with this, or we can just kind of take a little bit of a shortcut here. But basically what we want to do here is we want to have a volume formula in here. Now, the really simple way would just be to put pi r squared h, okay? But that doesn't quite cut it. Now, I'm talking about number 14 here. So we're in question 14. So the volume for 10 slices. Now, for 10 slices, we need to be a little fancier than this. So let's go 1 to 10. Now, the pi is fine. That'll be there. Okay, for the radius. What's the radius? Well, the radius is this right here, right? Well, isn't that just that function, that f of x that we had, right? Isn't that, now, I know there's 2 of them depending on the width, and we were averaging them. I'm not going to get that fancy about doing that. Let's just say we took one right in the middle or something. Let's say we took one right in the middle and we called that the radius. That would be about the same, right, as averaging them. Okay, but it'd be that function value right there. So instead of r, I'm going to put f of, now I'm not going to put anything in there right now, but I'll come back and do that in a second. So the f function of the top half of the lemon is like our radius. And you can see why we only want to do half. That's why we cut it in half here, because we've got that so we could get the radius, right? And then the h is going to be, we could just call that delta x, but for 10 of them, and let's take, I don't know, Ryan, what was your width of your lemon? Or the total?
6.4.
6.4. So for those guys, they would have 6.4 divided by 10 over here. Wouldn't that be the width for 10 slices? It'd be 6.4, it'd be the total width divided by 10. And for you guys, it'd be whatever your width was, divided by 10. Now, we could get real fancy in here, and we could go 6.4i divided by 10. That'd be the real fancy way to do it, right, for their lemon, right? So when i's a 1, the first slice would be 6.4 divided by 10. And then the second slice would be 6.4 times 2 divided by 10, right? and that's where we could evaluate our function, and then that height would be our radius. I mean, so if we really wanted to get fancy, we could do that. Or all I really care about, to be honest with you, is if you just wrote this: pi f of x sub I squared and delta x. That's what I really care about here. I don't care about all this stuff. We did that back in chapter 5 when we were doing all this and writing those sigmas and stuff, but I don't care about that. This is the part I care about. That you understand is that the sigma is adding up a bunch of volumes. Adding up a bunch of volumes. 10 volumes, or then go to the next line down, it could be 100 volumes, right? That's all you'd have to do for that next line, right? Is just change it to 100. Obviously the width would get different, we understand that, but I just want you to see this formula, okay? And then we can do an infinite number, so then what do they say there? Then later they say, what about an infinite number? Well, then we could just make this an n up here, right? And then we could do n goes to infinity out in front. We could do the limit as n goes to infinity, right? But that's a process we've already went through in chapter 5. Everybody okay with that? Right? And then, of course, once you do that, that turns into a what? An integral, right? And so that's the next question. It says, what general calculus name do we give to this infinite summing process? The definite integral, right? That's the general calculus name for an infinite sum. Okay, so it's like we're going to slice these lemons into paper-thin slices, and we're going to add up these volumes, and that should give us the volume of the lemon. Okay? What specific calculus expression for the volume of the solid generated by rotating your lemon curve about the x-axis that does not involve summation notation? Well, that'd be the integral. So we'll go integral. So for Ryan's lemon, it would be from 0 to 6.4. You guys adjust it for your own lemon. Okay? Pi, the f of x sub I squared would end up just being, now we called ours r of x, I think. You could call it f of x. I told those guys to save it in their calculator as r of x. I'm going to actually put r of x on mine, squared. You can call that function anything you want, f of x. I'm going to call it r of x, stand for radius. Okay? And then what's a delta x become? Just the dx. Now the interesting part of that, I'm going to go to a new page here. So we got the integral from 0 to 6.4 of pi r of x squared dx. To me, the interesting part of that is this part right here. That's just pi r squared. Is that a volume? Is that a volume equation right there? Pi r squared? Now think about it. Think about it. Is that volume, pi r squared? That's not volume. What is that? No. That's area. Why isn't it volume? We don't have the h. Well, what happened to the h? It turned into the dx. Well, you know what? We've seen that before. When we do our integrals and we have like miles per hour, and the dx is the hours, and then it gives us miles, right? So why does this give us volume? It's because this part is area, and then this part is thickness, right? Think about what gives you volume, right? Think about what gives you volume. Like this piece of paper. This piece of paper right here. It's got an area, right? That'd be the flat piece. But it's also got a volume, right? Because doesn't this have a thickness? It's got a very, very small thickness. But if I wanted the volume of this paper to be this area times this thickness, right? Be this area times this thickness. So what we're saying is to find volume, our integral, this integral is going to be volume. It's area times the dx is the thickness, but the thickness is becoming infinitely small. Okay? So this is going to be our formula. This is going to be our formula for finding the volume of a solid. If you want to write this down in your notes, we're going to come back and we're going to look at some examples here. Okay? That's going to be our formula for finding the volume of a solid by slicing. If we think of a volume of a solid by slicing, because and we'll go back and read one of those questions on our in those packets here in a little bit to finish up here today. But what you'll notice, it'll say find the volume of the solid generated by blah 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 revolving the region. I'll talk about that a little bit too. And then it'll say something something about, well, it won't actually say, it won't even say anything about slicing, but we'll know it's going to be by slicing. Then we're going to have some other ones that will say that a solid is formed with square cross sections perpendicular to the x-axis. Well, cross sections another name for slice. Cross sections another name for slice. Okay, so what we're going to do is our volume is going to be formed by setting up an integral where inside the integral we put an equation for the area of what the slice is. Now, what shape are our slices? The slices we just got to know they were circles. Now, don't say cylinder anymore. Our slices are circles. The thickness makes it a cylinder, but the thickness is the dx part, right? So now when we talk about slicing, we don't want to think about 6 lemon slices that are thick. We want to think an infinite number of slices, right? So if I took that lemon and sliced them really, really paper thin and held one up and asked you what shape is this, what would you say? You just said circle, right? You wouldn't have said cylinder, right? It's just like if I asked you what shape is this, you'd say rectangle. You wouldn't say rectangular prism, right? You wouldn't think about the thickness. You wouldn't call this a box. If I held up a cereal box, yeah, you'd say that's a box shape because it has thickness. This doesn't have really to speak of any thickness. So we'd call this a rectangle. So if I held up these wafer-thin slices, what shape is it? It's a circle. So we do the area of a circle in it. And that's why we have this pi r squared. So let's go back to that page. Let's actually do it on our calculators now. So I've went ahead and done it for these guys, or I've got it in here. Okay, I defined the radius to be that. So on your calculator, you can do that for your equation. Define r of x to equal that whole big mess of a thing. Okay, and all we need to do now, we want to do the integral. For theirs, it'd be from 0 to 6.4. It would be pi times, it would be r of x squared, and then dx. Right? And see how that's going to be volume? That's going to be pi times radius squared times height. The height is the dx. And cross your fingers. I got that. Now, is that remotely close to what you got with displacement?
Well,
Displacement got about 150.
yeah.
And then what about when you added up your 6 slices? 127 something.
Yeah.
Oh, that's interesting. Usually when we add up the slices and compare it to displacement, they're close, and this one's way off. Now, this, to me, a lot of times this one has the most room to be off. And that's because, think about it. You're tracing, how accurate was your tracing? How accurate is your measurement? You know, and then you're fitting a curve to it, which isn't going to fit perfectly. There's a lot of room for error in the mathematical part of this. Okay? The displacement's probably got some room for error too, but so that's not bad, actually. Anybody else getting closer or way off or something? How about you? What'd your other group, Riley, what'd you guys have for your displacement? 150 roughly? And what'd you have for your adding up your 6 slices? Okay, so and the lemons were pretty close to the same size. And now, have you done the equation yet? And what was that? 1 what? 39. So you're kind of all in that range. Okay, Noah, how about you guys? What was your displacement? Yeah.
That was 150.
Okay, and then our 6 slices.
Was like 152.
That's pretty good. And then did you do the integral? Anybody done the integral? I got it. We got 152. 152. So 150, 153, 152. You guys didn't win. What about you guys? Well, maybe. What'd you get for displacement for the water? 60, okay, and then when you added up your 6 slices? Okay, and then have you done the integral, anybody? Okay, let me know when you get your integral. Okay, now let's pull out, I don't know, 2011, what the heck. Let's grab that, grab your 2011 packet. Let me see if that's a good one. That's not a very good one. Let me see here. I apologize. I should have looked at this ahead of time.
Joseph Swenson.
All right. None of those are very good examples. So let's. That's not good. All right. Hang on here a second. I want to find a good. Grab that. Your homework's going to be in that LH packet that I gave you, the Chapter 7 LH packet, the little bit thicker of the LH packets. Yeah. Turn to page 419. Yeah, it's one I gave out a while back. Last week sometime. Yeah, it's this one right here. It's got to be 7 in the front. This one right here, it says 7 up in the top right hand corner. Okay. Turn to page 419. All right. Now, so let me just show you this example here. So what we're doing here, the reason when you get to these problems, it says find the volume of a solid by revolving a region. And let me show you why it says it that way. Let me pull up. This is pretty cool way to see these. But okay. All right. Okay. All right, so here's what we're talking about. So think about what we did. In these problems, we're going to say find the volume of the solid when this region is revolved around a certain axis. So when we look up here on the board, this would be the region they would give you. They would give you this function right here. You would draw it just like when we were doing area problems. You would draw that region. And now we got to imagine this two-dimensional flat region here revolving around the x-axis. You know, if you go to Hobby Lobby and you buy party decorations, you know, like the little wedding bell thing, you know what I'm talking about? They're folded flat. like different shapes. They're full of flat, and you open them and they open up, and then they the turkey and then the tissue paper, and you can get like bell shapes. So, like if you bought one, it would look like this. Oh, might look like this. It kind of come up like this, and then do that, right? Then you unfold it. It would be like a bell, right? Well, that's what we're talking about. In other words, we're talking about a two-dimensional. We're talking about a two-dimensional shape that would revolve and create a three-dimensional object. That's what we're talking about. So up here on the screen, we can see it a little better here. So imagine, so think of this dark red as our slice. Think of this as like our lemon region. If I revolve this, that would be like one slice. So you see the cylinder shape, right, of the slice. And, oops. So here would be like an example of 5 slices, like when we did that. Now what we want is actually an infinite number of those, right? We want an infinite number of those. So if I reset that, and let's look at this. Okay, now somehow I should, that's not where I went. Close enough. All right, so watch what happens when I revolve this, right? I create a three-dimensional solid. Now, and think of those paper-thin slices. So if I sweep that through there, so we would think about adding up, our integral is adding up all of those slices. So what you're going to draw is just going to be a two-dimensional shape. Let's reset that. What you will draw is just your region, like we've already been doing. And notice the strip, right? We're going to draw in a strip, but that strip is going to represent our radius. So when we work a problem like this, we will imagine this being revolved and creating a solid like our lemon. We will imagine the circular slice that's in there, but we'll understand that this strip is what part of our slice? The radius of our slice. And how will we find the length of that strip? Top minus bottom. So in this problem, the function is y equals square root of x. So this would be the top y value. So what I will write down is I'll write r equals the top y value minus the bottom y value, which in this case would just be 0, right? This is called your axis of revolution, where you're revolving your solid. Sometimes I'll draw a little, arrow like that to represent that. So that is our r. So when we go ahead and set up our integral now, we know, because I said earlier, our formula is this. It's the area of a slice times the thickness of the slice. Well, when we revolve this, we're going to create what shape of a slice? A circle. What's the area of a circle? Pi r squared. But what's our r? This right here, because it changes. The radius over here is littler than the radius out here, right? So that's why our r is always an equation, okay? So we're going to end up with pi, and then we're going to have this squared, right? We're going to have r squared, and then dx is the thickness. And in this problem, it would go from, what is that, 2 to, what is that, 9? 2 to 9. Okay, the strips fill the space from 2 to 9, but we're not doing just the area of that space. We're doing the area of that space, and we just want the length of the strip times the width of the strip, right? That'd be the area of the strip, and the integral would add up all the strips. And so then it would just be square root of x dx. That's all it would be, right, to do this area. What we want is the volume of all of these slices. And the way we get the volume of the slices is the area of the slice times the thickness of the slice. That's how you get volume of the slice, and the integral adds them all up. Since the slices are circles, we want the area of a circle, so that'd be pi times the radius squared. This strip is the radius of the circle. Let's look at it again, okay? Sweep it. Okay? This strip right here is the radius of a slice. Okay? So that when we do top minus bottom here and get that length, that is our radius. We put it into the formula pi times radius squared, and the dx is the thickness, and the integral adds them all up, and that's how we get volume. Okay, there it is. Yes.
So the top minus bottom, that's not really going to be that useful. It's just the x-axis, right?
Well, to start with today, because we've just introduced this, we're going to do simple ones. All of our things are going to be on the x-axis.
So are we going to make like stuff that's like for range?
Yes. Matter of fact, let's just do it right now. Okay? No, it's actually easier than you think. But all I have to do is move my axis of revolution down to here. Watch what happens. Creates a whole different solid. Now, remember, when we find these volumes, we're finding the volume of the solid material, not the empty space in between, right? But see that solid? Now look at the slices. What shape are the slices? Rings or donuts or washers, whatever you want to call it. Well, our formula says we got it in the integral, we want the area of the slice. Well, we're going to need the area of a ring. So we'll have to do the area of a ring in our integral for problems like this. Right? And that's not hard. The area of a ring's not hard. We can do that tomorrow. But, so if we move the axis of revolution off of the axis, the x-axis, then all of a sudden we got some empty space in there. And so then we will have different types of shapes. And that's what we'll deal with over the next several days. And we'll really get into it tomorrow. So you've got a very small number of assignment homework problems on it. We got the sheet handy, the homework sheet. It's the next line, the 419 line, is the third group down. There's 5 problems. 1, 2, 4, 9, and 10. 1, 2, 4, 9, and 10. And basically every one of those, they show you the region, they put the strip in there for you, and basically the strip is the function, and the function is the radius. I mean, every one of them is going to be pi r squared dx. I mean, every one of them. And the r is the function. I mean, it's really that simple. But tomorrow we'll really focus in on understanding this, what's going on. Maybe you do already. I mean, it's very simple. The integral is adding up the volume of all of these slices. Okay? Of what's going on. All right. So those 5 problems for tomorrow. Now, we also may talk about that step-by-step packet. On that step-by-step packet, use your calculator on some of that. If you get to some of those equations that get really kind of nasty solving, even though it said no calculator, go ahead and use it. Yeah, there was one that was quite it was nasty. Well, I don't know if it was quite nasty. That's a high bar.